Welcome back to Science to Sleep By. Find a calm, comfortable space, breathe gently, and let your mind drift across the quiet frontier of our universe. Tonight, we explore a mystery gliding through the dark, an object from another star, known as 3I Atlas, and the surprising NASA data suggesting that its slow, steady rotation might mimic the kind of artificial gravity we dream of building for future space habitats. This is Science to Sleep By, where the wonders of the cosmos meet the gentle rhythm of rest. And as always, this journey is crafted with care for my listeners across the United States, inviting you to unwind, to imagine, and to let curiosity ease into serenity. When we look into the night sky, most of what we see belongs to our own cosmic neighborhood. The planets, the comets, the asteroids, even the faint dust drifting between worlds, all of it has shared the same long, slow orbit around the sun for billions of years. But every so often, something unusual appears. Something that does not belong to our solar system. Something that comes from far beyond the comforting pull of our sun's gravity. One such visitor is known as 3I Atlas, the third confirmed interstellar object ever detected by human instruments. Its arrival was not dramatic or blazing. Instead, it came quietly, almost shyly, moving with a gentle and ancient patience, as though it had drifted for so long through interstellar darkness that it had learned the art of calm itself. Imagine this moment: astronomers scanning the skies with the Atlas system, a network designed to detect dangerous, near-Earth objects, suddenly notice a faint point of light moving slightly differently than the thousands of others they monitor. It is subtle at first, just a small motion that doesn't fit the normal pathways asteroids usually follow. Most local objects obey predictable curves shaped by the sun's gravity. They loop around our star in carefully balanced orbits, returning again and again with steady devotion. But this one moves in a way that appears unfamiliar. Its path is open, not closed, as though it is merely passing by, not staying. That is the first clue that this might be something rare. Something born in another star's cradle, far beyond our own. To understand how exceptional this is, consider the vastness between stars. Even traveling at unimaginable speeds, an object moving freely through interstellar space may take millions of years to cross the distance between one stellar system and the next. It must endure radiation storms, collisions with dust grains, the cold loneliness of empty voids, and the slow erosion of cosmic time. By the time it wanders close to Earth, it has already lived a history longer than humanity itself. The remnants of this history are etched into its surface, in the dust it carries, in the way it rotates, in the scars and grooves smoothed by eons of drifting. And so, when 3I Atlas finally reached our solar system, it was not arriving as something new, but as a timeless traveler finally coming into view. NASA's first datasets revealed just how unique this visitor is. Its velocity, its angle of entry, and its hyperbolic trajectory all point to an origin outside the sun's gravitational influence. This means 3I Atlas is not a leftover fragment from our solar system's formation. It is a relic from somewhere else, a piece of another cosmic environment with its own history, its own rules, perhaps even its own planets orbiting distant suns. That alone gives this object a profound sense of mystery. It is a message in a bottle from the galaxy itself, drifting into our presence after a journey no human could ever personally experience. To visualize its passage, imagine the solar system as a calm pond reflecting starlight. In this serene picture, the planets move like slow ripples expanding outward from the center. Everything within the pond belongs to it. But then, from somewhere far beyond the edge, a small pebble skips across the water. It creates a disturbance not born from the pond's own patterns. Its splash is foreign, unfamiliar, and instantly noticeable. That pebble is what an interstellar object represents. It is a disruption not caused by the sun, but by some distant gravitational event in another star system, perhaps long vanished or transformed. As 3I Atlas approached, telescopes tuned carefully to detect its brightness. These variations in brightness, sometimes rising, sometimes falling, help astronomers understand its shape and rotation. Early readings suggest it might be elongated, like a stretched stone worn smooth over countless millennia. This shape mirrors other interstellar objects previously observed, raising questions about whether long cosmic journeys tend to sculpt objects into these peculiar forms. The difference, however, lies not only in shape, but in movement. 3i Atlas drifts with a steady, almost graceful rotation, as though it learned to conserve its motion across millions of miles without any interference. This peaceful stability only adds to its mystery, hinting that its internal structure or external forces have kept it rotating in a balanced, predictable way. Its approach also brings with it the faintest whisper of another world. Every interstellar object is believed to originate from a different solar system, ejected violently during early planetary formation or gravitational reshuffling. That means 3i Atlas is quite literally a physical piece of another star's story, carrying within it the chemical fingerprints of alien environments. Though we cannot touch it or sample it directly, its color, reflectivity, and rotational behavior provide gentle suggestions about what materials may lie on or beneath its surface. Some astronomers speculate that interstellar objects may contain rare icy compounds, exotic metals, or structural features not commonly found in our own solar system. Others propose they might be fragments of once thriving planetary systems, remnants of worlds that may have flourished or collapsed long before Earth formed. As 3i Atlas moved deeper into our solar system, the sun's faint pull gently altered its path. But its trajectory remains hyperbolic, meaning it is not captured. It is simply passing through, borrowing a moment of our cosmic stage before continuing its endless route back into interstellar night. This brief encounter offers scientists a rare opportunity to study something that humanity may encounter only a handful of times per century, if that. Interstellar visitors like this are incredibly rare, and each one carries a treasure of information about worlds unimaginably distant. Even its calm rotation, even its dimness, even the slight drifting motion of its light curve, all of it becomes a clue, a whisper, a hint of the galaxy's deeper secrets. And for those who listen closely, it becomes an invitation to explore more, to wonder more, and to let the quiet majesty of the cosmos settle gently into the mind like a lullaby. When NASA first began gathering data on 3i Atlas, the observations appeared ordinary at a glance. A small point of reflected sunlight, a dim signature against the black velvet of space. But as researchers watched the object over several nights, a gentle rhythm emerged in the measurements, a kind of celestial pulse that rose and fell with an almost metronomic calm. What they were seeing was the rotation of 3i Atlas, revealed not by direct imaging, but by the subtle changes in the brightness of the light it reflected. These variations are known as a light curve, and for astronomers, they serve as the heartbeat of a distant object, telling a story of shape, spin, and motion. The light curve of 3i Atlas didn't just display a rotation, it displayed a smooth, steady pattern that stood out immediately. Most small bodies in our solar system rotate in ways that are irregular, chaotic, or tumbling. They wobble because of uneven mass distribution. They spin with unpredictable speeds because past collisions have jolted them into erratic movement. They are restless, constantly adjusting to gravitational nudges from planets or the sun, jittery as they drift through the solar system. But the rotation of 3i Atlas seemed different. It wasn't hurried, nor was it stumbling. Instead, it carried a sense of deliberate consistency, as though it had been spinning with the same gentle cadence for a very long time. This quiet steadiness caught NASA's attention. Light curves that repeat with such clarity often indicate that an object is elongated or shaped in a way that creates distinct areas of brightness and shadow as it turns. But what made the case of 3i Atlas unusual was not just its shape. It was the mathematical cleanliness of the pattern, the way the brightness rose and fell with such graceful repetition. This suggested that the object might be rotating as though it were being guided by an internal balance, or perhaps by external forces that had shaped its rotation long ago. When researchers plotted the light curve into predictive models, the rotation rate appeared to settle comfortably into a range that, intriguingly, mirrors the spin rates engineers propose for generating artificial gravity in future human-made space habitats. This does not mean 3i Atlas is artificial, but the coincidence is striking enough to invite curiosity. For NASA scientists, who are trained to examine anomalies with caution and humility, the rotation was simply another data point requiring explanation. Yet the resemblance to known engineering principles created a quiet ripple of interest, particularly among specialists studying rotational dynamics of both natural and artificial bodies. A rotation that produces consistent centrifugal force is unusual for objects born in natural environments. Over time, collisions, thermal stresses from starlight, or an even outgassing of ices tend to disrupt smooth rotation. Even comets with long histories often have chaotic motion. But 3i Atlas, despite being shaped by forces experienced in another solar system entirely, seemed to have resisted these disruptions or returned to a steady state. Some scientists suggested that perhaps it had not experienced any major collisions for millions of years, allowing it to settle into a peaceful equilibrium. Others wondered whether the gravitational field of its origin system might have imparted this rhythm long ago, locking it into a spin that continued unbroken across interstellar distances. NASA's infrared instruments added more details, capturing how heat radiated from the object. This helped refine models of its surface. The thermal data implied a surface that isn't perfectly uniform, yet the variations did not seem to affect the rotation the way uneven surfaces typically do. Normally, when sunlight heats different areas unevenly, the resulting thermal recoil can subtly change an object's spin over time. But with 3i Atlas, those effects appeared muted, as though the object had either lost volatile materials long ago or developed a stable enough shape to keep those forces balanced. The consistency of rotation also raised questions about internal structure. Solid monolithic bodies can maintain stable rotation if they are dense and uniform inside. Rubble pile asteroids, which are loose collections of rocks held together by weak gravity, often rotate irregularly because their internal components shift under stress. If 3i Atlas is rotating so smoothly, it might mean that it is not a fragile pile of debris, but something more cohesive. Perhaps it formed near the inner regions of another star system, where heat fused its materials into a stronger whole. Or perhaps it was once part of a larger body that fractured in a way that left this smaller piece structurally sound. These are quiet mysteries, the kind that do not demand immediate answers, but instead offer a gentle invitation to wonder. NASA's data also captured hints of how the rotation might be slowly changing. There were small, almost imperceptible deviations, suggesting that some force, however slight, might be nudging the object as it travels. These forces could be natural, such as residual outgassing from trapped ices deep within, or they could be the effects of the sun's gentle push as radiation pressure interacts with its surface. Whatever the source, the changes were faint enough to preserve the overall smoothness of the rotation, maintaining the object's graceful turning through the void. Astronomers often describe interstellar objects as time travelers, carry ancient momentum across unimaginable distances. The rotation of 3i Atlas reinforces this image. It is as if the object has been turning quietly for so long that the motion itself has become a kind of cosmic meditation. Layer by layer, the data reveals a traveler that does not wobble wildly, does not tumble unpredictably, but instead turns with the slow composure of something shaped by vast stretches of time. For NASA, this rotational signature is more than a curiosity. It is a key to understanding the forces that act on interstellar objects and the environments from which they originate. Each turn, each change in brightness, each thermal gradient becomes a data point that helps map the geology, structure, and history of a visitor formed beneath an unfamiliar sky. And so, with every night of observation, the rotation of 3i Atlas becomes clearer, unfolding like a quiet story, told in the language of light, motion, and time. A story that continues to drift through the darkness of space. With Comcertain Tito, understand why NASA scientists reacted with such quiet fascination when they noticed the rotation of 3i Atlas. We must drift gently into the concept of artificial gravity, dream that has accompanied humanity ever since we first imagined traveling among the stars. In the stillness of space, where there is no natural downward pull, our bodies lose muscle strength, our bones thin, and our sense of balance shifts in ways that feel unnatural. For long-term spaceflight, gravity is not just a luxury, it becomes a necessity. And so engineers have long studied how to recreate it, not by using mysterious forces, but by relying on something deeply familiar: rotation. The idea is simple enough to picture. If you spin a bucket of water, even slowly, the water presses outward against the walls, as if it has weight. This outward push is the result of inertia, the tendency of objects to keep moving in a straight line unless something redirects them. In a rotating habitat, the curved wall constantly redirects the occupant's motion, pushing them outward. That pressure feels like gravity. It creates an artificial downward pull that the body interprets as weight, allowing humans to walk, sleep, and live more comfortably during long voyages. Although the idea is straightforward, the physics behind it are elegant and precise. The amount of artificial gravity produced depends on two factors: the radius of the rotating structure and the speed at which it turns. A larger radius allows for a slower rotation, creating a gentle downward force without causing the dizziness that rapid spinning induces. Engineers often imagine massive cylinders, hundreds of meters wide, slowly rotating once every minute or two. Inside, people would stand on the inner surface, feeling pressed gently toward the floor. The ground would curve upward at the edges, creating a horizon that loops around you. And somewhere in the center, motionless and weightless, would be the dead zone where no artificial gravity exists at all. To those studying 3I Atlas, the connection to this concept arises because its measured rotation aligns strikingly well with the range used in theoretical artificial gravity designs. The coincidence is not a conclusion. It is simply an observation, like noticing that a drifting log happens to spin at the same rate as a human-built wheel. But coincidences can inspire deeper exploration, not by jumping to answers, but by encouraging us to understand the foundations more clearly. Artificial gravity through rotation is not merely hypothetical. NASA, along with other agencies, has spent decades examining the physiological effects of long-term microgravity and exploring how rotation might address them. Early experiments in the mid-20th century involved centrifuges and rotating rooms designed to test how quickly humans could adapt to a spinning environment. These experiments revealed that slow, large radius rotations create minimal discomfort. Too small a radius, however, and the rotation must be faster to produce the same gravity, which leads to motion sickness and disorientation. The ideal solution involves building habitats large enough for the rotation to feel almost imperceptible, allowing residents to live and work without the constant awareness that the world around them is spinning. Science fiction has embraced this concept for decades, often depicting vast cylindrical worlds quietly turning in the darkness, their cities arranged around the curved inner surface like a ring. The International Space Station, although not large enough to rotate, uses exercise-based countermeasures to slow physical deterioration. But future missions to Mars or beyond may require rotating modules or full-scale spinning habitats. Engineers imagine connecting spacecraft with long rotating arms or designing inflatables that expand into circular living spaces. All of these concepts share one principle: rotation equals gravity. The physics that govern this process also govern objects in space. Any asteroid or interstellar object that rotates will produce centrifugal effects along its surface, though not enough to mimic Earth-like gravity. Instead, the forces are often weak, barely measurable, but they still influence how loose material settles across the surface. Dust, pebbles, and fractured pieces sometimes migrate slowly toward areas of lower energy, creating subtle ridges or belts. A more stable and consistent rotation can help maintain a predictable surface environment. While chaotic, tumbling can scatter debris or destabilize the object over time. With 3I Atlas, NASA scientists noted that its rotation falls into a calm and steady range that, if the object were significantly larger and hollow, would be ideal for generating artificial gravity. Of course, 3I Atlas is not a megastructure. It is a natural object, small and faint, but the resemblance is enough to spark curiosity, especially when paired with the object's smooth light curve and mysteriously stable behavior. Studying these features gives researchers valuable insight into how rotational forces shape bodies in deep space, how internal composition affects their dynamics, and how time itself molds their movement. Another important aspect of rotation-based artificial gravity is the preservation of equilibrium. A structure must rotate consistently without wobbling or precessing, which means its mass must be distributed evenly or stabilized by engineering. Natural bodies can achieve stable rotation too, but often only after millions of years of tumbling, gradually resolve into a calmer spin. This process is influenced by collisions, gravitational interactions, and the thermal effects of starlight heating the surface. The fact that 3I Atlas rotates so predictably suggests that it may have reached a long-term equilibrium, one preserved across the vast, lonely journey between star systems. When considering the physics of rotation, one must also imagine the sensory environment it creates. On a spinning habitat, the downward direction would always point outward. The stars would appear to drift across the sky in gentle arcs. Even subtle movements would interact with the rotation, creating unique sensations. Engineers must calculate how objects fall, how balls bounce, how water behaves, and how people move. Rotation becomes an all-encompassing experience, defining not just gravity, but the rhythms of daily life. When scientists wonder about the rotation of 3I Atlas, they are not simply measuring its spin. They are imagining the internal stresses, the equilibrium points, the way materials settle, and the long-term processes that shaped it. And so, the theoretical foundations of rotation-based artificial gravity weave together the simplest of principles with the deepest of cosmic implications. By spinning, a structure can create a sense of weight where none exists. By spinning, a natural object can reveal its internal harmony or its ancient past. And by spinning, 3I Atlas offers a calm, steady signature that aligns both with the elegance of physics and the quiet wonder of a visitor from beyond our sun. When NASA scientists first recognized the smooth, measured rotation of 3I Atlas, an almost philosophical question emerged, not spoken loudly, but quietly shared across research rooms, observatories, and late-night conversations among astrophysicists. Could an object wandering from another star system be rotating in a way that resembles the engineered designs of human-made habitats? It is not a suggestion of origin or intention, but rather an exploration of coincidence, a coincidence so striking that it invites deeper thought. The same way one pauses when a stone naturally fractures into a near-perfect shape, or when rivers carve valleys with astonishing symmetry. Nature is capable of astonishing precision, and yet there is intrigue in an alignment so close to the very rotational patterns we ourselves calculate for artificial gravity. To imagine this, picture a vast cylindrical station in space, the kind dreamed of by engineers and authors across generations. Such a habitat rotates slowly, providing centrifugal force strong enough to mimic gravity, yet gentle enough to remain comfortable. The rotation period of these habitats often lies between 1 and 3 minutes per full revolution, depending on the structure's size. This balance, the sweet spot between too fast and too slow, is essential to avoid dizziness, disorientation, or uneven gravitational effects. Now consider 3I Atlas, drifting alone across the void. Early NASA data hints at a rotation period curiously nestled in this same region. Not too hurried, not too lethargic, but calm and consistent, resembling the very cadence we would aim for if we were building a place for humans to live among the stars. This resemblance does not imply design. Instead, it sets the mind wandering toward the remarkable possibility that forces shaping the cosmos might naturally produce such a rotation. Just as wind can shape dunes into repeating patterns, or ocean waves sculpt coasts into smooth curves, the laws of physics are universal, governing everything from spinning galaxies to rotating space stations. Under the right conditions, with the right balance of internal structure, external nudges, and timeless motion, an object can settle into a stable spin that mirrors the precision of engineered rotation. To analyze this possibility, scientists look first to the object's shape. Early brightness curves suggest elongation, perhaps a stretched, spindle-like form, similar in some ways to Oumuamua, the first interstellar visitor detected in our solar system. An elongated body will naturally rotate around its axis of least inertia, producing a steady, predictable rate unless disturbed. Over millions of years, small influences like radiation pressure, gravitational tides, or distant collisions can either accelerate or slow this spin, but often the cumulative effects guide the object toward equilibrium. When 3I Atlas arrived near the Sun, it appeared to be in such a state, as though it had been calmly rotating for a tremendous span of time. NASA's light curve analysis shows a pattern of brightness variations that repeat smoothly, suggesting the rotation is not tumbling, chaotic, or shifting unpredictably. Instead, it is uniform, like a well-balanced gyroscope. This reminds engineers of the way artificial habitats must be designed to avoid precession, of the wobbling motion that occurs when rotational forces are misaligned. In human-built structures, this wobble is corrected through gyroscopic systems or carefully distributed masses. But for a natural object, long-term cosmic processes must do this work, settling, reshaping, and dispersing an even mass until a peaceful rotation emerges. If 3I Atlas has achieved such a rotation naturally, it offers a powerful example of how stability can arise spontaneously, even in the endless quiet of interstellar space. Another factor that draws attention is the smoothness of the rotation period. Normally, small bodies exhibit irregularity due to surface jets, volatile materials, or thermal forces. Cometary objects, in particular, can erupt in bursts of gas as they heat near a star, causing their spin to jitter slightly. But with 3I Atlas, the available data hints at a rotation largely unaffected by such disturbances. Some astronomers suggest that perhaps it lost its volatile materials long ago, burned away during previous approaches to other stars, or stripped by cosmic radiation over millions of years. If the object is now mostly rock and metal with little left to escape as gas, then its rotation would remain steady, unperturbed by internal pressures. This consistent rotation further raises questions about its internal structure. If 3I Atlas is solid, its spin would remain smooth. But if it is a loosely bound rubble pile, the motion of internal components could create shifts and wobbles. Yet no significant wobble appears in the data so far. This steadiness again places its behavior near the realm of engineered objects, which are intentionally built to maintain their rotation without internal disturbance. While nature can certainly produce such uniformity, the rarity of such perfect stability makes 3I Atlas an unusually compelling case. The idea that it rotates like a habitat prompts an intellectual exercise. What if, in some distant future, humanity were to construct a long-term outpost in deep space? The rotation would not be fast or forceful. It would be patient, gentle, reliable, just like the measured cadence seen in 3I Atlas. The resemblance is poetic, connecting human aspirations to cosmic realities, suggesting that the engineering concepts we develop here on Earth echo patterns that already exist across the galaxy. It is a reminder that our designs are not separate from nature, but inspired by the very geometry and motion the universe has demonstrated for billions of years. In addition, this alignment invites a sense of cosmic symmetry. The same principles that govern a rotating stone drifting between stars govern the spinning wheels we imagine for future colonists. The universe, indifferent and vast, sometimes mirrors human ideas in subtle ways. Not deliberately, but harmoniously, as though the physical laws that shape the galaxies also whisper hints of what is possible for civilizations seeking to join the stars. When engineers look at the rotation of 3I Atlas, they see not just an object, but a reflection of the physics they rely on, a natural embodiment of rotational stability. And so the question lingers in the background. Could 3I Atlas be rotating exactly like a human-made habitat? Not as an assertion, but as a contemplation, a quiet thought that bridges the gap between natural formation and human imagination, between the ancient journeys of interstellar travelers and the futuristic visions of humanity's long-term presence in space. It becomes a gentle reminder of how the universe shapes itself, how rotation becomes a universal language, and how patterns born from stars can mirror the dreams of those who look up at them with curiosity and wonder. When astronomers first turned their instruments toward 3I Atlas, they were not looking for anything extraordinary. Interstellar objects are rare, but not impossible, and each one that wanders through our solar system is an opportunity to learn something small yet meaningful about the nature of distant worlds. But as the faint light from 3I Atlas reached NASA's detectors, something subtle and intriguing began to reveal itself. It was not loud, not dramatic, but gentle, like a whispered pattern carried across a vast distance. This whisper came in the form of a light curve, the delicate record of brightness rising and falling as the object rotated. Light curves are more than just measurements. They are the language through which distant objects speak, telling astronomers about their shape, surface variations, and rotational geometry. With 3I Atlas, the story written in its light was both soothingly regular and deeply mysterious. The first thing scientists noticed was the rhythm. As 3I Atlas spun in the darkness, the reflected sunlight fluctuated with a consistency that is unusual for objects of its size. These fluctuations are caused by the way its shape interacts with incoming light. A spherical object would reflect light in a nearly uniform manner, producing only slight variations as it turns. But an elongated object, something shaped more like a cigar, a shard, or a spindle, creates deeper contrasts between its sides. When its broad face turns toward Earth, it appears brighter. When its narrow edge rotates into view, the brightness falls. The depth and frequency of those dips reveal a surprising amount about its geometry. Early analyses suggest that 3I Atlas is not a round or evenly shaped body. Instead, it appears stretched, perhaps dramatically so, elongated in a way that gives its rotation an almost theatrical effect. In the data, peaks of brightness rise as the wider surfaces reflect sunlight, only to fade again as thinner edges take their place. This repeating cycle creates a pattern that scientists can translate into estimates of length, width, and proportions, like reconstructing a sculpture from nothing more than the shadows it casts. And in the case of 3I Atlas, those shadows hint at a body that may be several times longer than it is wide, a shape reminiscent of other interstellar visitors, but still uniquely its own. Yet the shape is only part of the mystery. The consistency of the light curve makes it clear that 3I Atlas is not tumbling chaotically, as many elongated objects do. Tumbling would distort the rhythm of brightness, creating irregularities and unexpected peaks. Instead, the rotations of 3I Atlas appear calm and predictable, suggesting that its internal mass is distributed in a stable way. This is surprising because elongated shapes often have mass concentrated near their centers or irregularly positioned along their bodies, which normally leads to wobbling. But here, the wobble seems faint at most, almost unnoticeable. It is as though the object has settled into a natural equilibrium over millions of years, gently aligning itself into a rotation that conserves energy and preserves stability. This stability also raises questions about the object's internal makeup. If 3I Atlas were a loosely bound rubble pile, the slight gravitational interactions it experienced during its long journey might have caused shifting among its components. These shifts would appear as minor fluctuations or chaotic signatures in the light curve. Yet the data shows a smoothness that implies cohesion, some degree of structural integrity, suggesting that its internal composition could be more solid, perhaps monolithic or fused over time through heat, pressure, or ancient impacts. In the silent stretches between stars, where collisions are rare and erosion is slow, such cohesion might last for eons, preserving the shape even as the object drifts through emptiness. Surface features also contribute to the light curve's subtleties. If an object has bright patches, dark regions, or reflective materials distributed unevenly across its surface, these details would produce secondary variations in brightness. With 3i Atlas, some faint hints of surface variation may exist, but nothing overwhelming. The dominance of the primary rhythmic pattern suggests that its geometry, not its coloration or texture, is the main driver of the brightness changes. This makes the object feel both simple and mysterious. Simple in the sense that its shape tells most of the story. Mysterious because the shape itself is so unusual and precisely expressed in the light. The geometry, if elongated, invites speculation about its origin. Elongated objects can form from tidal forces near large planets, from violent collisions that shatter larger bodies into slender fragments, or from gradual erosion that sharpens one dimension more than another. If 3i Atlas formed in another star system's early chaotic era, its shape could be the fossil of a dramatic past, a shard blown away from a larger parent body, or a sliver formed when planetary material collided during the violent stages of planetary formation. Over time, its edges could have been smoothed by countless micro-impacts, its surfaces darkened by cosmic radiation, leaving behind a streamlined, symmetrical form. But there is another possibility that scientists consider quietly, without certainty. Some interstellar objects, because of their elongated shapes and smooth rotational signatures, resemble concepts long used in human engineering, particularly those related to spacecraft or rotational habitats. Of course, nature can produce elongated bodies of many kinds. But when the shape aligns so well with principles of stability and equilibrium known from engineered designs, it creates a moment of reflection. Not a leap to artificiality, but a curiosity about how the same physics that guide human creations also operate in the natural world. The resemblance becomes a reminder of how deeply embedded these principles are in the structure of the universe. Brightness curves also reveal something about surface texture. If the surface is rough, scattered reflections create small inconsistencies in light patterns. If it is smoother, the curve becomes cleaner. 3i Atlas displays a light curve that is relatively smooth, suggesting either a uniform surface texture or one that has been worn down over time. Interstellar dust, cosmic rays, and temperature extremes can gradually erode sharp edges and refine surfaces, leaving behind a weathered, almost polished body after millions of years adrift. The deeper astronomers study the light curve, the more it resembles a kind of cosmic fingerprint, unique, detailed, and quietly expressive. It speaks of geometry sculpted by time, rotation, shaped by balance, and a journey traced across distances so vast that the object's very shape becomes a record of its past. The mystery lies not in whether the object is natural or artificial, but in how perfectly its shape and movement align with stable rotational principles, producing a light curve that is both scientifically rich and aesthetically serene. In this way, 3i Atlas becomes not just an object to study, but a gentle reminder of the harmony between form, motion, and light that exists throughout the universe. To understand why 3i Atlas has captivated so many scientists, one must look beyond its path, its composition, or even its interstellar origins. The fascination deepens when its rotation, structure, and motion are compared with something humanity has long imagined, but has never successfully built at full scale: an artificial gravity generator created through rotation. This concept, both elegantly simple and engineeringly challenging, forms the heart of theories about future space habitats. And strangely, the quiet, consistent spin of 3i Atlas echoes precisely the kind of rotational signature needed to mimic gravity in deep space. It's this overlap between a natural interstellar traveler and humanity's most ambitious engineering dreams that makes Keynote 6 so compelling. Artificial gravity through rotation is not science fiction. It's physics, calm, predictable, and grounded in concepts that students learn in their earliest studies of circular motion. When an object spins, anything on or within it experiences a force pushing outward, a sensation similar to gravity, even though it arises not from mass pulling inward, but from motion pushing outward. This outward force is called centrifugal force, and while it isn't a true force in the fundamental sense, it behaves like one, creating a downward pull for anyone standing on the inner rim of a rotating habitat. For astronauts living inside such a structure, the experience would feel like gravity, steady and reassuring, allowing their bodies to function almost as they do on Earth. The critical ingredient in this design is rotation. The speed of rotation, the radius of the structure, and its mass distribution all work together to determine the strength and stability of this artificial gravity. Too fast a spin, and the force becomes disorienting, creating nausea and instability. Too slow and the effect becomes negligible, leaving astronauts vulnerable to the harmful consequences of weightlessness. To create a comfortable artificial gravity, the rotation must fall into a precise range, not too aggressive, not too weak. This sweet spot is a balance that nature rarely achieves on its own. Yet 3I Atlas appears, intriguingly, to occupy a rotation rate that sits well within the boundaries known to generate stable centrifugal force. The rotation period of 3I Atlas, as measured from its rhythmic light curve, is slow and consistent, an ideal candidate for generating a gentle outward push. In engineering terms, it rotates at a rate comparable to the spin of a theoretical space habitat designed for long-term human habitation. This is not to suggest that 3I Atlas was built for such a purpose, but the alignment of its rotation with artificial gravity models is striking enough that researchers take notice. If an artificial structure were intended to simulate gravity, it would need to rotate in a smooth, predictable pattern to maintain comfortable internal conditions. And smooth, predictable rotation is exactly what the data from NASA shows. Another consideration is the shape of the rotating structure. The most efficient artificial gravity designs rely on elongated or circular forms, shapes that allow for the distribution of mass around a central axis. A rotating cylinder or spindle-shaped object naturally encourages the outward force needed for artificial gravity. In this sense, the elongated profile suggested for 3I Atlas fits surprisingly well into the mathematical models. Elongation is not only ideal for stability, but also for structural integrity during rotation. The motion of such a body distributes stress evenly along its length, allowing it to maintain shape even over long durations of spin. But rotation alone does not explain everything. For artificial gravity to work, the object must not tumble or wobble excessively. Tumbling creates unpredictable shifts in force that would send objects floating unpredictably inside a structure. Astronauts inside a tumbling habitat would experience sudden lightness or heaviness, or even sideways forces that would make life unlivable. To avoid these issues, an artificial gravity habitat must rotate around a stable axis, with minimal oscillation. What makes 3I Atlas stand out is not just that it rotates cleanly. The light curve shows a rotational profile almost free of chaotic variation. It exhibits the characteristics of a peacefully spinning object that has found equilibrium in its motion. Whether this equilibrium is intentional or simply the result of millions of years drifting through quiet space is a question that may never be fully answered. Interstellar objects are shaped by physics over unimaginably long timescales. Gradual processes like collisions, gravitational nudges, and thermal changes could coax a body into a stable spin, smoothing out irregular movement until only the simplest and most energetically efficient rotation remains. In this way, nature itself can sculpt an object to mirror the rotational clarity that human engineers seek for artificial gravity. The parallel is poetic, reflecting how universal the laws of motion truly are. The internal structure of 3I Atlas is also important when considering artificial gravity. The centrifugal effect depends heavily on how mass is distributed. If an object's mass is concentrated unevenly, the rotation becomes unstable, leading to wobbling or precession. But the data suggests that 3I Atlas does not exhibit significant wobble, which implies that its mass may be more evenly distributed than expected. A uniform mass distribution is uncommon for natural rocky bodies, which often have loose aggregates, cavities, or uneven density. That 3I Atlas rotates as though it is internally balanced makes scientists wonder what processes shaped it so evenly. There's another nuance. The slight variations in brightness in the light curve may indicate surface features or textural differences, but they occur in a pattern that is secondary to the main rhythm. This means that while small irregularities exist, they do not meaningfully affect the object's spin. This level of stability resembles the way an engineered structure maintains rotation despite minor surface imperfections. In human-built rotating habitats, designers account for small irregularities by ensuring that the main structure remains symmetrical, allowing rotation to stay stable despite cosmetic flaws. That a natural interstellar object displays a similar behavior is both reassuring and intriguing. Finally, the most fascinating aspect of studying 3I Atlas through the lens of artificial gravity is what it symbolizes. It reminds us that the cosmos operates according to the same principles that guide our engineering. The rotation that could generate artificial gravity on a spacecraft is the same rotation that shapes the motion of distant wandering objects. The same balance of forces that humans hope to harness for future space habitats is quietly at work in the depths between stars. And when an object like 3I Atlas drifts into our solar system, carrying a rotation that mirrors our most ambitious dreams, it creates a sense of profound connection between human invention and cosmic motion, suggesting that even our boldest ideas are reflections of natural laws playing out on a universal scale. When NASA first began tracking 3I Atlas, the mission was simple: collect data, refine the object's trajectory, estimate its rotation, and determine its physical characteristics through the faint light it reflected. These steps are standard for newly detected interstellar visitors, and yet, the more data NASA collected, the clearer it became that this object carried with it a pattern unlike the majority of natural wanderers humanity has encountered. What emerged from the observations was a rotation that seemed too calm, too steady, and too precise for an object shaped by chaos and time alone. But, as is often the case in astronomy, the story hides in the details, written softly in the numbers and curves that measure the ancient motion of something that has crossed unimaginable distances. Before passing briefly near our sun, NASA's observations began with the object's brightness measurements. To the eye, the light from 3I Atlas is nothing more than a dim point drifting across telescopic fields. Yet sensitive instruments transform that faint sparkle into a graph, a light curve capable of revealing the object's rotation, shape, and even hints of surface texture. As the data accumulated night after night, a gentle pattern emerged. The brightness rose and fell in a smooth, repeating rhythm, echoing the motion of a well-balanced spinning object. Such smoothness is rare among natural bodies. Most asteroids wobble slightly as they rotate, the result of uneven mass distribution, internal fractures, or past collisions. But 3I Atlas showed no signs of that erratic behavior. Instead, its rotation resembled a stable dance, guided by an internal balance that seemed almost deliberate. NASA's infrared and optical readings confirmed that the object's angular momentum, the measure of how much rotational energy it carries, was unwavering over the period of observations. Angular momentum only remains stable when an object is free from significant disturbance and possesses an internally cohesive structure. If 3I Atlas were loosely packed, like a cosmic rubble pile held together by weak gravity, small deviations in its spin would appear as irregular brightness changes. These are common among near-Earth asteroids and even some large main belt objects. Yet NASA's instruments captured no such deviations. 3I Atlas rotated as though its interior were fused or solid, maintaining its motion with the grace of something shaped by long-term equilibrium. One of NASA's key findings came from comparative brightness analysis, where data from multiple instruments and observation windows are layered together. What scientists found was not a chaotic series of peaks and troughs, but a consistent waveform that repeated with an almost soothing rhythm. Each cycle revealed the same patterns, the same orientation shifts, the same alignment with its rotational axis. This level of consistency often points to a natural object that has been smoothed by time, an object that has drifted for millions, perhaps billions, of years until only its most stable rotation remains. But there was still something more. The amplitude of the light curve suggested a body elongated enough that its rotation should create detectable wobble, yet it did not. Instead, it spun like a balanced baton, moving through the void, maintaining an orientation that allowed its brightness signature to play like a gentle pulse. NASA also used thermal modeling to estimate how the object absorbs and releases heat. Thermal data can reveal subtle irregularities, lumps, ridges, or depressions that create temperature fluctuations across a body's surface. These fluctuations can, in turn, disturb rotation over time. But 3I Atlas again defied expectations. Its thermal signature aligned smoothly with the light curve, suggesting that its surface, while not necessarily uniform, did not contain enough irregular variations to interrupt its rotational stability. Even more surprising was how the thermal data complemented the rotational readings, reinforcing the idea that the object's shape is elongated but structurally balanced, possibly more cohesive than typical interstellar debris. NASA researchers also examined the rotational phase shift, the slight variation observed when a rotating object is viewed at different angles or under different lighting conditions. Natural objects often show minor shifts as they tumble or respond to uneven heating. 3I Atlas showed none of the typical signatures. Instead, its phase alignment remained so consistent that scientists could predict its brightness at specific rotational points with high accuracy. This kind of predictability is associated with objects that have reached rotational equilibrium, where internal stresses have long settled and no further tumbling occurs. In the silent journey between stars, only the most stable spin survives. And 3I Atlas seems to have embraced that serenity completely. One of the most intriguing aspects of NASA's data is how closely the rotation rate aligns with theoretical predictions for artificial gravity systems. While there is no evidence that the object is artificial, its rotational frequency falls into a range that would produce gentle outward force if the object were large and hollow. This overlap between natural astrophysics and human engineering is one of the reasons the object is so captivating. It reminds scientists that nature and technology often share the same mathematical foundations, and that physical laws do not discriminate between the natural and the artificial. Whether shaped by intention or by the slow hand of cosmic processes, a stable rotation is a stable rotation, and the universe offers many paths to achieve it. NASA's spectroscopic readings also contribute to the story, showing that the surface materials reflect light in a way consistent with rocky or metallic compositions. While this alone does not reveal anything about artificiality or naturalness, when combined with rotational stability, it paints a picture of an object that is not fragile. Interstellar travel is harsh, and fragile bodies do not survive the journey intact. The fact that 3I Atlas not only survived but rotated with such grace suggests a composition capable of enduring extreme conditions over extraordinary timescales. As researchers analyzed more data from ground-based telescopes and space-based observatories, the object's motion appeared increasingly calm, almost meditative. Nothing in the data suggested chaos. Nothing hinted at violent internal fractures or sudden shifts. Instead, the object drifted into the solar system with the quiet assurance of something that had been rotating in darkness for ages. Its spin carried the signature of patience, shaped slowly and steadily by physics that operate with the same timeless precision everywhere in the cosmos. NASA's observations do not solve the mystery of 3I Atlas. Instead, they deepen it in the gentlest way possible, offering details that invite reflection rather than shock. The object's rotation, stability, and structural coherence create a scientific puzzle that unfolds like a soft melody, inviting astronomers to listen more closely rather than jump to conclusions. And as more data continues to flow in, the steady rhythm of 3I Atlas remains one of the most quietly fascinating features of any interstellar visitor humanity has ever studied. When astronomers observe an interstellar object like 3I Atlas, they know they are not merely studying a piece of rock drifting through space. They are studying a messenger from another star system, a traveler shaped by forces, events, and histories that unfolded far beyond the reach of our sun. Every fragment of data gathered from such an object becomes a clue to a cosmic story written across unimaginable distances and timescales. Among those clues, the rotation of 3i Atlas stands out as one of the most revealing. Its gentle, stable spin, its rhythmic light curve, and its unusual consistency invite scientists to contemplate not only the physics that shaped it, but also the world it may have come from, the journey it has endured, and the quiet testimony it carries about regions of the galaxy humanity has never seen. Every rotating object in space is the product of countless interactions. An object's spin can be shaped by collisions, by the gravitational nudges of passing worlds, by internal stresses, or by thermal forces. Over time, instability fades, wobbles settle, and rotational motion evolves into whatever configuration requires the least energy to maintain. In a sense, rotation becomes a memory of everything the object has experienced. For 3i Atlas, that memory is surprisingly calm. NASA's observations reveal a spin that is not chaotic or erratic, but steady, balanced, and continuous. Such a rotation suggests that the object has spent an extraordinary amount of time free from disruptive influences. Only an object that has drifted alone through placid interstellar space, untouched by strong gravitational fields or major collisions, could maintain such a serene motion. This suggests that 3i Atlas may have been ejected from its home system in a relatively gentle way. Many interstellar objects are kicked into space through violent planetary migrations or catastrophic impacts. These processes often impart irregular spins, chaotic tumbling, or internal fractures. But 3i Atlas does not show the signs of such trauma. Instead, its rotation implies an origin in a stable environment, perhaps a mature star system where dynamical chaos has already settled. It may have been dislodged through a slow gravitational interaction, perhaps nudged by the shifting orbit of a distant gas giant or by the evolving gravitational shape of its star as it aged. Such gentle processes could send an object drifting into interstellar space, without imparting the spinning disorder commonly seen in more violent ejections. The rotation also hints at internal structure. A stable spin suggests that 3i Atlas is not loosely held together like a rubble pile. Instead, it may be a consolidated fragment of a larger body, perhaps a shard from the crust of an early planet or the remnant of a moon shattered long ago. Over millions of years, the pressures of temperature extremes and the slow erosion of cosmic dust could have smoothed its edges, refined its form, and coaxed its rotation into balance. The resulting object, shaped by time itself, then continued drifting, carrying with it the geological fingerprints of its home system. Its minerals, density, and structure may all encode information about the conditions present. As we reach the quiet end of this journey through data, observation, and cosmic speculation, the story of 3i Atlas unfolds, not as a tale of drama or sudden revelation, but as a meditation on the universe's subtle harmonies. This interstellar traveler arrived with no fanfare, a faint point of light drifting across our telescopes. Yet it carried within its rotation, its shape, and its steady rhythm, a story billions of years in the making. Each measurement, each fluctuation in brightness, each thermal reading serves as a whisper from distant stars, a record of processes and histories that unfolded long before our sun ignited, long before humanity even looked to the skies with curiosity. Its gentle spin reminds us that motion is not always violent, that equilibrium can emerge naturally, and that even in the vast chaos of space, there exist patterns of profound quiet and elegance. NASA's meticulous observations revealed more than just an object in motion. They revealed a lesson in patience and stability, showing how natural forces sculpt matter over unimaginable spans of time. The smooth rotation, the predictable light curve, the structural coherence, all of these features invite us to contemplate the physics of rotation, the principles behind artificial gravity, and the cosmic inevitability that stable forms can emerge from disorder. They also remind us that the universe often mirrors the ideas and designs that humanity later discovers. What engineers dream of as futuristic spinning habitats or artificial gravity modules has already been exemplified in nature. In an object traveling alone through the void, unobserved for eons, the rotation of 3i Atlas also serves as a bridge between disciplines. It ties together astrophysics, planetary science, orbital mechanics, and even human-centered engineering concepts. By studying the light curves and the thermal signatures, scientists can infer shape, mass distribution, and internal structure, all of which feed into models of interstellar object behavior. Yet perhaps the most profound aspect of 3 Atlas lies not in the technical data, but in what it inspires in the human mind. Its calm rotation, precise alignment, and elegant geometry offer a moment of quiet reflection. They remind us of the patience inherent in cosmic processes, the beauty that arises without effort, and the harmony that can persist over vast distances and times. For scientists, engineers, and dreamers alike, it is a gentle invitation to look beyond the immediate, to appreciate subtlety, and to find awe in motion that is slow, deliberate, and enduring. In the stillness of interstellar space, 3I Atlas drifts on, carrying its secrets, its rotations, and its quiet story, a testament to the intricate balance of nature and a reminder that even the smallest points of light can hold lessons far greater than their size might suggest. Its journey, measured and measured again through telescopes, sensors, and models, becomes a meditation on time, distance, and the shared laws of physics that govern both distant wanderers and human ingenuity, quietly bridging the gap between the cosmos and our dreams of the stars.